10.1, use properties of tangents. Essential question, how can you verify that a segment is a tangent to a circle? We'll learn quite a bit about this during the second half of this lesson. First of all, some vocab that we have to lock down here before we continue. Circle. Circle really is a set of points, a given distance from a given point. So if you kind of visualize a circle being formed by a set of points the same distance from the center, we have ourselves a circle. So a good definition of a circle is a set of points, a given distance from a given point, where that given distance is known as the radius and that given point is known as the center of the circle. So the center of a circle is the point equidistant from the points of the circle. A radius is a segment from the center to the circle. It also refers as a measure as well. So radius, denoted R, it looks like that. Plural for radius is radii. A diameter, we'll come to in a moment here, but we'll go ahead and do a chord. A chord is a segment with endpoints on the circle. So chord, I have an endpoint here, an endpoint here, there's a chord. Now a diameter, if you take a look, does that, we can call that a chord that contains the center. It's also the longest chord in the circle. Now a secant looks like this. Here's our circle, here's a secant. So secant is a line that hits a circle twice. Alrighty, moving on here, a few left. Now a tangent is a segment line or ray that hits a circle once. So here's an example of a tangent. There's my circle. I'm going to have a critter like that, and this point that it hits is known as the point of tangency. Now we'll talk a little bit later why they use the word tangent for this, and we use it in trigonometry as well. Coplanar circles, circles in the same plane, and common tangents are lines, rays or segments that are tangents to more than one circle. So we can say tangent to got a circle here and a circle here. Here's an example of a common tangent. Oh boy. Hits here and hits here. So not that great of a drawing. Now our first practice problem here is go ahead and identify some of these critters. So tangent AB with point of tangent CA. So I can go ahead here. And it's tangent line, so I have to make it a line. A here and B can be anywhere else. Center C, do your best to eyeball it. Put the letter C off to the side here. Radius CA, it's right there. Put an R there. Secant DE. Secant hits twice, and I'm going to use these points here as naming. Diameter EF. So diameter's got to go from E here straight across here. So I'm going to go ahead and connect them up. And this has to be F here. And then chord EG. Chord EG. I'm just going to make a segment with another endpoint here. I got EG. Some more problems here. We have use the diagram here. The radius of A is 3. So 3. The diameter is going to be 3 this way as well. So that's 6. The radius of B, I could go up. That's 2. The diameter of D, it looks like 2. Oh, actually that's 4. I didn't go all the way across. So it's 2 here and 2 here. So radius is 2. CD's distance is 1. BA's distance is right here. That looks like 5. And the area of a circle, you should recall this from your past mathematics, is pi r squared. In this case, my radius for A is 3. So we could call that 9 pi, or about 28.3. And that would be in square units. Theorem 10.1, in a plane, a line, segment, or ray is tangent to its circle if and only if it is perpendicular to a radius of a circle at its endpoint on the circle. So really what we're saying is, hey, if we got a tangent whatever, point of tangency here, this has to be a right angle. 10.3 here, common tangents here. Now circle A and B. Now it's going to look like this. I'm just going to redraw them down here. I have 1 common tangent, 2 common tangents, and a sneaky one here, so this has 3. C and D, these are referred to as externally or internally tangent circles. And really the only tangent I've got is right there. So this has 1. Now B and C, I've got a circle B and I've got a circle C. And now do the tangents. These ones are pretty straightforward here. But I also have some kind of internally tangent. So that looks like 4. One there. As we continue here, again, this one goes back to our central question. What's the deal with tangents here? Now we're hoping that this angle is a right angle. So the question is 3 squared plus 4 squared equal 5 squared? And the question we should say answer is yes, because we have this. So we'll say yes, okay? We have forms a right triangle. And with that right triangle, we have a right angle. Okay, and And with that right angle, and this is a radius, then we can go ahead and say we have a tangent. Kind of an offshoot of this problem is this question, find the radius here. Well, we know that this is a tangent because of this and this being a radius. So now we can go ahead and still use the Pythagorean theorem. But we need to be careful here because the hypotenuse is this whole length, r plus 8. Now we must be careful here in solving this algebraically for r, as we need to FOIL this binomial square. So again, that's really r plus 8 times r plus 8. So we FOIL, and we get r squared, 8r plus another 8r for 16r. So the O and the I terms are identical and they add up to 16r, and we get 64. Now from here I can subtract off r squareds from both sides. I can subtract this 64 over. I get 80 equals 16r, and after a divide step, I get r equals 5. Now last theorem here, if we have a circle and we have an external point and I do tangents that both hit that, we end up with congruent segments. So these are called tangent segments to an external point are congruent. Now with that in place, I can go ahead here, if we're told that we have tangents, that means this is congruent to that. So 3x equals x plus 12. Subtract that x over to the left. Divide by 2. And we get x equals 6. That concludes our original notes for section 10.1.